So this one is going to be 1, 2, 3, 4, 5, 6, 7, 8, 9. So for V2, what I'm going to do is I'm going to erase this. I'm going to put V2 over here, leaving everything else the same. That motion vector is gone. All right, for this, just for this test. So that means that now that I have this new motion vector in here, it means that D is now going to change, because now this block goes to some other position in the adjacent image. I get a new D. Now what is this smoothness term over here? So the smoothness term is now this motion vector minus this one minus this one, this one minus this one, this one minus this one. Obviously you don't really need to calculate this one, right? Because that's what we took it from. It's not 0, there's something wrong. And you do it for all of them. That gives me E2. All right. Do the same thing for E3. E4, you're going to take the motion vector again and put it here. And you're going to calculate the data term, you're going to calculate the smoothness. So now you have 9 possibilities for that block. Okay, so the assumption here is that maybe the current block is wrong. Maybe the motion vector to the current block is wrong. Maybe the neighbor will help us. Maybe the neighboring motion vector is correct. This is actually not a bad assumption, because what happens is sometimes you have an image that has a smooth region. And above that smooth region, there may be an area that has a lot of texture, an area that has like a lot of pattern. So maybe you saw from the obstacle flow thing that we did, you noticed that the motion vectors were good except in those regions that were smooth. Remember the calendar, some areas of the calendar, let's see. Remember like these big red areas up here and the yellow areas on the goat? You should see more random motion vectors in those regions for a smaller window. Once you got a bigger window, you were okay. So what about on the edge? So let's say, for example, that there is an area maybe over in this area up here, there's a lot of texture, and it is next to a smooth region. Well, if all the motion is actually in the same direction, then we can actually use the motion vector from the texture region for the smooth region. So it may actually be a good estimate. But we're not guessing, because we're testing all of this. If we make an assumption, we choose a particular motion vector, we're going to test it in that energy minimization framework to see if the error is less. If the error is not less, we're not going to use it. So we lose nothing by trying that. All right. So that's the way you form the 9. And then your goal is that you're going to choose the V that has the minimum error. Okay. And the way that this is written, you should get familiar with this kind of notation. You guys familiar with that notation? Maybe not. I'm going to go explain it. So this argument, so the man is probably easy to understand. If I didn't put the argument here, then I would actually be looking at E and not P. So the argument basically just says that I want to find the V in this framework that minimizes the whole thing. But what I'm returning is I'm returning the argument, not the actual value. So if I put some V in here, it gives me some value, right? That's the E. But here, by putting R, it's saying that I want to put the V that gives me the minimum value. All right, so you can actually just do, if you wrote it like this, this would be another way to look at it. So by putting arg there, I'm returning the actual V. That's just a notational thing. So when you see that in papers, you'll understand it. Okay. So one other thing I want to talk about with this is that you'll notice I actually chose all of the candidates. So I chose, all 9 of these. But why did I do that? I mean, why not just look at, say, this guy, this guy, this guy, this one, this one? Why not just the horizontal and vertical neighbors? Why did I look at the diagonal neighbors as well? So